Yeah, it's better with microphone on. Okay. So yeah, a little bit talk about modulators, frequency comms at the beginning, which could enable this type of terahertz synthesis. I'm going to mention a little bit about this as well, and advertise 2 clear talks from my group that are actually going to talk more about this year, and then talk about some frequency shifting and quantum transduction if there's time, and then, as I mentioned, maybe a little bit about HyperLight's offering. So I'm assuming Amir yesterday talked about lithium niobate, so everybody knows everything about lithium niobate at Stanford. I just real quick mention that we are working on this platform using thin film lithium niobate, and we are trying to make advantage of large second order linearity of lithium niobate that allows us to make very fast modulators, frequency converters, photon pair sources, and things like that. In the context of today's talk, I'll mainly talk about the electro-optic application, basically where this second order linearity allows you to mix one RF photon with one optical photon and to generate other optical photons, or maybe different frequency generation, as you'll see, where 2 optical photons can generate RF, for example. The platform, this is just to make sure everybody's on the same page. Lithium niobate, we heard today that what was niobium is silicon of superconductivity. So lithium niobate has been referred to as silicon of optoelectronics because it has enabled many important academic and industrial breakthroughs in a kind of basic transduction between electrical and optical fields. This cross-section of bulk lithium niobate modulator based on Mach-Zehnder configuration, when you have 2 optical waveguides defined by doping of bulk lithium niobate. Of course, Artifair is the king of bulk lithium niobate. So probably you are already familiar with some of these concepts. And basically, if you put electrodes on lithium niobate, you can take advantage of strong electro-optic coefficient to increase the phase velocity of one of these waveguides and reduce the other one. And then when these 2 waves that propagate to different waveguides meet, they can be adding constructively or destructively, which gives you 0 or 1, basically gives you electro-optic modulation or optical signal. Over the last 10 plus years, us and many others, most notably Amir in this university, have basically pushed this platform based on thin film lithium niobate that allows us to define a waveguide by reactive ion etching that makes optical modes a lot more confined and allows us to bring electrodes much closer, which improves performance of the devices, increase the bandwidth, and many other good things. Also in integration, you can put more components on the same chip that actually improves complexity, what we can do. And so I think this has been known in the community for a while, that actually by etching lithium niobate you can take many advantages, improve significantly our bulk platform. But what people haven't been able to do for a while was actually realize low loss waveguides using this reactive ion etching lithium niobate. And so that's something that we've done already, I don't know, 8 years ago, demonstrated that these losses can be on the order of 3 dB per meter, and we can make ring resonators with the quality factors on the order of 10 million. Recently, losses are on the order of 1 dB per meter. I should point out these are multi-mode waveguides. We are really just trying to see what is the limit of the platform here, like of this lithium niobate and insulator platform. And together with Tobias Kippenberg, we kind of guesstimated that limit of this particular lithium niobate and insulator with particular, when their particular oxide and lithium niobate cut was on the order of 200 million. Okay, so there's still some room to improve fabrication processes to get there, but this kind of quality factors are plenty good. Day to day, we get 5 to 10 million without trying a little hard, but kind of this kind of 30 million we need to put a little bit of effort into, and also hope that cleanroom is in good shape. Yes. Okay. So with this, then we kind of did many interesting things. Modulators, frequency comms. I'll talk a little bit about these today. Isolators, I will not talk about. Frequency shifters, I'll talk about. Resonator-based frequency comms, I'll mention a bit, and curve frequency comms more recently. So These are all, except for this one, it's all electro-optics. And we also have periodically lithium niobate for frequency conversion for quantum communications, but I'm not going to talk a lot about this. So big deal for this modulation, which is actually, I'll touch upon this in the context of like commercializing this towards the end, but big motivation for this work was that actually we can make modulators. It can be driven directly by CMOS voltages, like so voltages below 1 volt or so, which is essential for what is the main application of this platform in optical communication, be it for data center communication, be it for long-haul telecommunication. So this is basically where we think this is going to make most impact, but also this kind of 100 gigahertz. By the way, the lithium niobate chips operate with bandwidths exceeding 500 gigahertz easily, but the electronics and packaging basically limits it to about 145 at the moment. And of course, what Christina showed, we can also go to terahertz. Like electro-optic response is very, very fast, so we can go to high frequencies. So in a lab, what we've been doing, just FYI, some fun stuff we've been doing, which maybe is not so interesting here. I forgot to delete the slides, so bear with me. It's this electro-optic modulator that's simultaneously digital tunnel converter, because when you go to very high frequency, very high bit rates, you actually, it's not so easy to have very fast and inexpensive digital tunnel converters. So what we have done, we took Mach-Zehnder interferometer, chopped the electrodes. Well, the interferometer is the same, but the electrodes are chopped so that each one is half as short as the previous one. And then if you bring this bit stream, like basically ones and zeros, to the arms, to these electrodes, you actually do not need any DAC anymore, digital tunnel conversion, because basically the most significant bit has the longest electrodes, so it's going to make the most phase shift. And the least significant bit of this 4-bit word has the shortest electrode, so it's going to make the least amount of phase shift. And when you put it all together, you can get essentially to drive this with binary signal and get analog output. And so we have then implemented this through HyperLight's multi-project wafer run. So basically, this is a 6-inch wafer that was fabricated, and then of course has a bunch of these modulators. I'm not going to go through the detail, but basically you can then use this to synthesize digitally all of these sequences. For example, waveforms, right? So this is sine wave that's synthesized just by sending 4-bit words, squares, sawtooth, whatever. So it's we actually use it quite a bit now for various applications. You can use this also for microwave signal processing, make microwave delay lines, which is what these two charts show here at the bottom. Also today, I think John was mentioning this kind of nice transduction process where you can drive, so basically radio over fiber approach, where you modulate the optical signal and then detect it at distance, in this case at the bottom of the fridge, using high-speed detectors. In collaboration with Andreas Bailing a few years ago, we actually integrated some of these MUTC modified unit traveling carrier photodiodes that actually have bandwidth until thin lithium niobate that's exceeding already 100 gigahertz, for example, and they have demonstrated even higher bandwidth. So basically here is, this is kind of communication link that's mildly useless because we have modulator and detector right after it. But if you separate them, with a little bit of fiber, then you can actually do some interesting stuff. But nice thing is, in this way, you can make transceiver on the same chip, and potentially, if you pull these things down, it can be of interest for driving maybe some of these high-speed, high-frequency qubits. We have also made these phase and amplitude modulator in shorter wavelengths, and this is at 737 nanometers. So for some of to control the spectral and temporal profile of our silicon vacancy color centers, which is another research that we do. It's very similar to what Jelena is actually pioneering. Has done beautiful work at Stanford, also combining lithium niobate with this silicon vacancy for frequency conversion. So here, the reason I'm mentioning mainly in context of this presentation is that basically by using phase modulator and driving phase modulator with sawtooth, which is so-called Ceradan technique, or basically by kind of timing RF pulse to kind of optical pulse to ride the wave or RF signal, you can actually, you can shift the frequency of your optical wave up or down, in this case by 30 gigahertz, okay? And then basically if you go shift up and shift down, now you have 60 gigahertz range And this efficiency of this is actually pretty high, optical efficiency. And insertion loss is very small. So you can just now beat these two signals to generate very efficiently 60 gigahertz tone. Right? And so this shift could also be larger. That would allow you to synthesize terahertz signals, for example. So this is work we are just wrapping up for publication. How you can make even more shift is basically you can now put this basically the way you can think about this is let's forget about this amplitude modulator that essentially carves pulse out of CW signal, and then basically come in with the pulses through phase modulator. And so you apply RF signal that, and this is traveling wave phase modulator. So essentially this phase velocity of microwave signal is the same as group velocity of optical pulse. And so if now you time your optical pulse to be on a rising edge or trailing edge of microwave signal, you can get frequency upshift or downshift. But you go only through resonator, through phase modulator once. So now if you actually combine it, put it in a resonator, then you can go to the same phase modulator many, many times, and you can get cascaded shifting, essentially, right? So this is what we've done in this work, where we basically, we have switched, it's really, really fast. Eventually we'll add phase modulator here, as you will see. But for now, it's just basically Mach-Zehnder control ring resonator coupler. This, by the way, allows you to have this ring resonator coupled, critically undercoupled or super overcoupled. It's relatively, that has been demonstrated by others in this community as well. I believe Amir has some work in that regard as well. But what we can do now by controlling the switch, we can have pulse go straight. We can get pulse going and make one trip. We can go have pulse, these are experimental data. Have 2 trips, 3 trips, or I guess, I don't know. Yeah, okay, yeah, 4 trips, this is time. And so on and so forth, the basic, but every time because of the loss, you pick up a little bit of loss. Essentially, pulse density goes down. This Q of this resonator was the order of million. So if you go to our 30 million, then you can actually make many more shifts, many more round trips. So you can use this delay line, for example. But what you can do, if you actually put now phase modulator here, every time you go through it, you can shear it a little bit. And so that's what we've done here, for example. So each time pulse goes through, it gets shifted by some number of gigahertz. And overall, we were able to shift, for example, signal by 400 gigahertz one way or 400 gigahertz the other way. So now you have the 800 gigahertz separation from single optical pulse, essentially without, well, with some optical loss because of this. And if you beat them, you can get essential terahertz wave out of this. This is of interest. This could be combined, for example, combined with John's high-speed detectors at the bottom of the fridge to generate microwave signals there. Yeah, it's just this, but bigger. Okay, and so that's one way how you can kind of generate, starting from a single optical wave, you can shift it essentially some number of hundreds of gigahertz left or right. Another way, you can just generate frequency comp and then filter out comp teeth that you like. If you generate broad frequency comp, you can get basically 2 tones that are quite far apart. If you then beat them, you can generate terahertz waves. And the simplest way to generate actual frequency comp, it's also one of the first that people have demonstrated way back when, was actually using phase modulator. I think this was already mentioned, I think, by John today as well, as a parasitic effect. But for us, this is actually a super exciting effect. So you take phase modulator and drive it hard and generate sidebands. And typically, these sidebands are not uniform, as shown here. This is actually experimental data from one of the TFLN united phase modulator we built almost 6 years ago now. And so if you're making frequency comp for telecom applications, this kind of comp teeth need to be flat so that, you know, person that uses this channel versus person that uses this channel to communicate using wavelet division multiplexing actually have this, in this case, they wouldn't have the same signal to noise ratio, which is a problem, right? So you kind of need to flatten this comp. And the way you typically flatten this comp in the community, this is, I think, believe from Scott Idam's work, you take intensity modulator, combine it with 2 phase modulators, and these are typically discrete components, and then it gives you flat comp. So what we have done, we have integrated these on the same chip, and thereby overcoming essentially the insertion loss. You need to go to 3 different chips, essentially, in this case, and therefore we don't need amplifier in this case, for example. So you have 1 amplitude modulator, and here's 1 phase modulator, but we go twice through it. And that allows you to make really nice frequency comp. I'm not going to worry about coupling. So basically, this is experimental data that shows how if you drive this amplitude and phase modulator with, for example, 10 gigahertz to 30 gigahertz RF tone, we can make very, very broad frequency comb, and it's also very, very flat. And so now what you can do, you can come in, essentially filter some of these lines and use it in your terahertz synthesis. I'll mention this a little later. Another way to make even broader combs, if you want to separate things further, would be to put phase modulator inside the optical resonator. And then if you drive phase modulator with the same frequency that is the same as the free spectral range of the resonator, this process of cascading, making complete actually gets resonant enhanced. And that was something we've done some time ago. And then you get this really broad electro-optic frequency comb. And then we made some improvements without going into details. Basically, by using 2 ranked resonators, we were able to go from this kind of spectrum shown in purple to spectrum shown in blue, basically expand the bandwidth and increase the power that frequency comb can generate. So these are not flat, so not very good, useful perhaps for frequent communication or maybe for what this community may be interested. But what's very nice that these guys actually generate femtosecond pulses, right? So this is basically if you just do inverse Fourier transform, and because they have really wide bandwidth, basically we measured the pulses coming out of these guys are on the order of 300 femtoseconds, and this can be further reduced by expanding comb bandwidth or by compressing this pulse using a kind of chirp distributed Bragg reflectors, which we have also integrated, but I'm not showing here. So this is a way to make very short pulses if of interest. And the broadest comb we made in thin-film lithium niobate, following a lot of nice work that was done in community, and this was actually we really benefited from Kyul Yang's, who was Yelena's former postdoc, insight and knowledge in frequency comb space. We were able to realize thin-film lithium niobate octave spanning curve frequency comb that have basically free spectral range of the order of 500 gigahertz. So now, if you have 500 gigahertz diode, you could also beat these two and generate terahertz, or you could actually use electro-optic nonlinearity of lithium niobate to synthesize, to essentially do this beating, do difference frequency generation, which we are working on. You can also, this is just FYI, you can also combine a curve frequency comb with electro-optic frequency comb if you want to divide this spectrum down to make it into something that can be, like more useful, for example. So we have shown how we can go from 500 gigahertz comb, essentially 10 or 30 gigahertz comb, simply by sending curve comb through electro-optic frequency comb and dividing the FSR between 2 comb teeth using electro-optic effect. And so how would you use this? And this is work of my former postdoc Shima, who is now professor at Delft, and Hannah, who is still in the group. Basically, this was just simple phase modulator frequency comb that without any electro-optics, this is this non-flat comb. In this particular case, actually, it's probably better not to have flat comb because you don't want to waste power of your optical power into comb teeth that you don't want to use to beat, right? So in this case, we designed it so that 2 strongest comb lines are the ones that we want to beat. And so then essentially, then you filter these guys out. And then in this case, they were mixed, they detected and then mixed. And the mixer, essentially, we were able to get 136 gigahertz signal out of this, okay? So you can make the system more complex and more efficient by taking advantage of thin-film lithium niobate photonics platform, for example. Okay, so another way to do spectral shifting and also terahertz synthesis and detection as well is actually to use this concept of photonic molecule, which maybe Amir mentioned. Yes. I don't know because Shima we didn't finish it. She had to actually leave for Europe. Yeah, it's for non-scientific reasons and not outside her control, but related to, anyway, so better not to go further. I don't know if this is on Zoom, God knows who's recording. But yes, we live in an interesting world. Yeah, happy to elaborate over coffee. But she'll be at Clio, I believe, I hope, or if not, Hannah may present, and then maybe she continued at Delft this effort. Yeah, so basically, yes. So you will multiply noise, will cascade, right? and then, I mean, and that will result in basically, determine the noise of this thing. That also can be used. I don't know if I have this slide, but for example, HyperLight, and maybe I'll see if I have this slide. I'll show it. You can use this to actually make a really stable microwave source by dividing the spectrum down, and then maybe this can be then used multiplied back up to go to the high frequencies. But it's a little speculative at this point. I think I have a slide on that. Okay, for photonic molecule, Amir, did you introduce it? Okay, all right, then I'll bother you. Basically, so here again, we are looking for ways to shift light left and right. Okay, and so we are interested on one end. Well, originally we were not interested in millimeter wave synthesis, but we were, we are pursuing this with Christina's group, and we were mainly interested in making local oscillators for various applications, as well as making quantum transducers. That's kind of original interest. But as you'll see, we are pushing this down to 100 gigahertz as well. So photonic molecule, it's a relatively straightforward concept. You have ring resonator, this is transmission. You put two ring resonators that are coupled, and basically by controlling the coupling, you generate doublet, right? You have super modes. This is the same as two coupled quantum wells when these two modes couple. And by controlling the coupling between these two, by lithographically controlling how far apart these resonators are, you can actually control the split. And so the idea is for our transduction, as you will see next, we tune this to be the same as the frequency of superconducting qubit we are working with, and then we can just use qubit or drive qubit. That's what we have done recently. And so this is the molecule, photonic molecule that Yalvin has developed. And so we have used this, maybe I'll just show this. We have used this to shift light up to 30 gigahertz, for example. Maybe I'll just show this data here. So basically, this is 12 gigahertz shifter, this is 30 gigahertz shifter, bear with me. So basically, by controlling coupling between these two ring resonators and ring resonator with a waveguide and controlling RF power and RF frequency, you have full control of optical signal that propagates in the system. So in this case, for example, this is 12 gigahertz shifter, basically meaning these two guys were a little further apart. We put light here. This is experimental data. And then we apply RF power and we move all of the light to this frequency. There's very little light left here, basically, and the efficiency is very high. We're not calculating also coupling losses in this efficiency. And this is, you can go from this mode to this mode, or you can go from this mode to that mode. It's actually, you can actually send both signals here and here, and they will just swap. It's its own, which is actually quite cool, and we have demonstrated this in this paper. So here we are going from higher frequency to lower frequency resonance with also high efficiency, and then this just shows 30 gigahertz shifter, which these two guys are closer together. Basically, it's splitting to begin with 30 gigahertz. Then we were by controlling RF power. In color here shows how much light was shifted. So we started this frequency. And then as you increase RF power at about 10 milliwatt of RF power, we have 50-50 split. So this is like beam splitter, if you will. And then if you keep going with power up, you go to 100 milliwatt of RF power, you have full shift in this case. This is just the advertisement for if you guys are interested. We are now, like one issue with these things is that when you start firing up RF power, everything moves. It's like you have a microwave oven on a chip and things move. And quality of life with people doing these experiments is not very good. So, which is why we invested in photonic wire bonding tool that we now have at Harvard. It's part of NNCI. I think you guys are part of that too, I believe. So, strictly speaking, you can use this tool, or I'm happy to help bonding. But basically, we are doing photonic wire bonding of our devices to fibers, not to achieve great efficiency, but they're decent, like. Typical coupling efficiency from a fiber to waveguides is on the order of 2 dB. Best we've done, it's 1.5 dB. But it's really, quality of life is better because this is shifter, 36-hour operation. This is actually unrelated heat at the beginning, I believe, and just like stable. And you can now do experiment, especially if we are doing quantum shifting. We are shifting single photon fields, and this is super important because we integrate for a long time. So this is just, a small advertisement. And yes, there's mechanical relief that you need to kind of induce, basically this, and then they operate in cryo. They don't break. So are they stable? We haven't tested them in exceeding, like right now, our transducer experiment, we have one fridge. So the Diamond people were doing stuff for last year plus, and now we are back in the transducing business, and all the transducers are now photonic wire bonded. And so we'll hopefully find out that they are stable, but it's possible that they are not. Yeah. But it took some effort to make them cryo compatible. But they haven't done long. Yes. So in LARPA Lumos program, we have pushed 1 watt through these things at room temperature. So far, we haven't. This was done with Freedom Photonics, their tool. So we haven't tried it here. This is more than what Vanguard specifies. It actually gets better with higher power because you start curing the polymer further, and it actually improves over the time. Yeah. Yeah. With this tool, I think this is pretty like the best. Actually, so on Lumos, Freedom Photonics bonded HyperLight chips, it was laser to fiber, laser to lithium niobate to fiber, 2.5 dB altogether. So if you split it, which is probably unfair because laser to chip is probably better, let's say 1.25. Ours best is only your 1.5. And before you guys get too excited, it doesn't work so well in visible. So for visible, we are making lenses using this approach, which work okay at the moment, not super great. Okay, and so then we were actually for completely unrelated, completely non-quantum reasons, we started looking into 100 gigahertz shifters, but then we packaged it now, like just for you, as a terahertz synthesis opportunity. And so this is actually, I just seen very nice work from Amir's group, a single resonator based transduction, I believe, right? So here we are still using a molecule. We couple 2 resonators, so the splitting is 100 gigahertz. And then we want to make shifter out of it at room temperature, but we are now considering going cold as well. So this was all done with normal metals. And so, okay, so this is what we are envisioning for this particular application. To generate terahertz, and you can run this in reverse to synthesize terahertz. And so we have, this is optics, so we can make molecule that has splitting of 100 gigahertz. These are modes that are 100 gigahertz split. They have decent Qs of intrinsic, I think, so 1 million, 2 million. So that's because you make smaller rings and strongly coupled, so it wasn't clear that's going to work. We can tune them. This is passive lithographic tuning, which I think it's oxymoron, but we make intentionally 2 rings different size so that we have Vernier effect. So we pick the ones that we want. All right. So, but also you can apply DC field and tune them, which we haven't. And then we also put, I think that was following some nice works with Dave and John, basically, we designed some 100 gigahertz or so RF circuitry and tested them. And so we can get resonances of the Q in the order of 100 at room temperature. And so would love to put this into these 3D cavities, cool it down, and there's David some, and try that, for example. So that would be one thing we would like to do. How am I doing? Yes, on time. Everybody was doing an hour lecture, so please keep that in mind. But
have shorter time of one.
Yeah, it's okay. People can eat fast, but this is yeah, I think still good, right? Yes, there was a question. Excellent question. Actually, in another experiment, we intentionally use molecule to. Okay, so actually that's not what you asked, but that's what I heard. Let me answer what I heard, and then I'll try to answer what you asked. Thermal drift is something that people often worry about, okay, and it's global. And so actually, if you do differential measurement, if you do measurement here and here, you actually eliminate that. So for a lot of our dirty secret about lithium niobate that we try not to be so secretive is that doesn't have it's not very stable at low frequencies. And so we have a lot of activities, so it doesn't mean measuring these things. And these are really painful experiments that we also benefit from photonic wire bonding. And there we choose to work with these photonic molecules because that eliminates thermal or global shifts and allows us to study exactly what you pointed out. So Okay, so now you asked, is this going to be a good device? So with DC bias, I mean, we see this kind of charge transport. Fun fact, and I'll show this later, when you cool it down, all of this freezes. So this is like, amazing. Cool it down, things work better. So yeah, I don't know, maybe I answered your question. Yeah, okay, good. Yeah. All right, so transducers. Basically, okay, so you have two fridges, you want to connect them. You can build giant tunnel that's cryo-cooled, which I thought was crazy till I just visited Fermilab. That's exactly what they're doing over many, many kilometers. So maybe not so crazy. Also, Walvar's group is building these things. There's a bunch of us in the community that are pursuing, and you've seen some talks today already, and yesterday, I'm sure we talked about this, looking into ways to do quantum transduction, essentially take microwave signal to optical domain, and then use optical, essentially go to higher energy photon, and then do communication with optical fibers, which could also benefit from all infrastructure that's being developed for modular quantum computing in general. So we think that basically this kind of making these interfaces between light at different frequencies is important. And in our case, we are pursuing this kind of transducer based on electro-optic effect, essentially on photonic molecule. And there's, of course, you can do this piezomechanically, and you can go biomechanics and optics as well. I guess just a little bit about transducer. So, now we actually made the transducer microwave circuit out of superconductor. So everything's going to operate at low temperature, and it's triply resonant process. So we have two ring resonators that are coupled that generate doublet, and now resonances are peaks. And apologize, they used to be dips. And then we have RF circuit that has resonance. That's basically should be in resonance with this splitting. And then this needs to be in resonance with the qubit sitting in a resonator. So there's a lot of resonances to be tuned, which is non-trivial, but HANA manages. And this system with pump, with decent amount of power, can get into cooperativity of 1. Okay. So that's good. Right now, when we started this business first, and actually we had this paper here came at the same time. I didn't reference Amir. Okay, I need to put. There was another paper from Amir, the same, basically coordinated submission. Efficiency transaction was 10 to the -5. Okay, which was pretty low. But with some work recently that HANA has done, just coming out in Nature Physics, actually 2 days ago, I believe, a transducer efficiency is 1.2%. And we already have chips that should be giving 10% just based on optical improvement, packaging, minimize. Which packaging is good because minimizes number of optical photons that are being like sloshed around the fridge, so you can actually put more optical power. So this is why we like packaging as well. Okay, so this is the so-called paperclip resonator geometry. We have two nested ring resonators, racetrack resonators. They're intentionally different size, so we have again this Vernier effect. So we pick two resonances that have splitting that we want to minimize the amount of tuning we need to do. Then we have superconducting resonator, and this is just performance, controls we can apply by applying DC. We can control the splitting. This is microwave losses are limited by piezomechanics, as originally actually reported by Amir's group, and so this is why these Qs are relatively low, but good enough to give us good cooperativity and good transaction efficiency. This is just characterization of microwave to optical, optical to microwave conversion. For different power levels. This is the bandwidth, added noise, which is pretty good. And then what we did, we basically got some qubits from Rigetti that in retrospect were not very good qubits. I guess they never expected us to actually go this far. So some of you guys are showing coherence today. Like I was like a little embarrassed, but that's what we got. And so basically we did. I like to say, like, essentially, it's like we take laser pointer, point it in the superconducting qubit, and we control it. Right? It's like controlling a cat with a laser pointer, sort of thing. So basically, transducer generates microwave at the bottom of the fridge. You can use detector as well, like what John was talking about. And then you basically use this microwave signal to control qubit, and we can do, coherent control. We concluded that our approach does not negatively impact qubit, but also our qubits were so bad that probably so we cannot really conclude a lot, but at least they were not worse than they were starting with. But nonetheless, this was actually, we're very happy that this first time introduced qubit in our system, and so now we're actually working with Will Oliver's group and hoping for even more impressive results. Okay, maybe I'll skip this in interest of time, and then maybe I'll just like now take advantage of all you being here to do some selling. Okay, so earn my keep at HyperLight. So I'll try to be hopefully useful. So HyperLight is TFLN chiplet TM company. We are in a business not building boxes, but we are building chips and wafers that we sell to different customers. It's about 50 people at the moment, pretty significant revenue by selling these modulators. It's a Central Square in Cambridge between MIT and Harvard. So if you're ever in Boston, please do come and visit. We would love to hire Stanford students. So far, it's been a local crew. These are some package modulators we sell. Current flagship is 145 gigahertz modulator. And we have 110 gigahertz IQ modulators, ultra low Pi. It's all CLO band, which is 1.3 or 1.5 micron range. These are standardized products. We have devices at 1 micron. We have customers at 780 and RGB, but they are not standardized. So if you want to work at different wavelengths, we can do it. This guy actually, Thorlabs buy from us, and then they put it in a bigger box with a nice display, and then charge it 3 times the cost. And so this sits inside, basically. They also had a laser, okay? And then for us, this is small, it's high margin, small volume market. But for us, the name of the game is basically getting into data center and AI communication. And so here is some prototype made a few years ago. This is thin-film lithium niobate chip that sits in so-called pluggable that basically saved server operators about 30% of power by basically replacing silicon photonics with thin-film lithium niobate, because you can use drive voltages are smaller, but also you can use less powerful laser because insertion loss is much, much smaller. That actually turned out to be an important thing. I figured maybe, that you could care about this guy because it's kind of 10 gigahertz, and this is terahertz, and this are millimeter wave, and this is millimeter wave workshop. As I said, now there's a version at 145 gigahertz. I was originally not going to show this slide, but because John showed the RF or radio over fiber application in cryo, I want to point out, for example, some work we've done in collaboration with PSI, Ed Ackerman's team. Basically, what they did, they took this ultra low Pi modulator. Pi here is 0.7 volts, but this is lower frequency. And they replaced standard modulator they used, that they built actually. And they immediately seen, because of low Pi and lower insertion loss, 15 dB improvement in the gain. So here, basically what you have, this is used for 5G, 6G antenna remoting and stuff like that, where basically you have some RF signal coming from the antenna. You put big beefy laser through it with low noise, and then you modulate modulator. So then this analog signal is an optical carrier, and the other end you detect it. What John did, he put it in a cryostat, basically. And here synthesize RF signal. And so you would like to have gain, not loss. Most of the time you do is there's no gain. In our case, also there's no gain, but it's less no gain than in competition. Okay, so this is actually pretty impressive. These guys are impressed. I was like, why is this good? There's no gain, but they like it. So, and then more importantly, you improve the noise figure. So noise goes down by 15 dB just because you have a lower Pi, a better insertion loss. So maybe of interest. That's what I was saying when you guys were asking about noise. So this is another thing that was developed in standard product. This is phase modulator that has phase Pi 1.5 volts at about 40 gigahertz. So what they did here in collaboration with the HQ Photonics, basically they made really stable microwave oscillator. Okay, so what you do, this is actually a startup for Care House group. So they have 2 very stable, I think they have a brilliant lasers that are some distance apart, and then you use some voltage control oscillator, you apply a microwave signal, you cascade the noise. That's what Ziza was asking. You add more and more noise, okay, when you make this EO comp on both sides, but then you detect this noise here and lock it back. And so this essentially cuts noise down tremendously. And the name of the game here, having low Pi and high frequency, so you can actually make as many compete as you can to cascade. You want to cascade noise as much as you want, as you possibly can. So when you divide it back, actually, with a large number, the noise goes down. This was amazing, actually. We got people ask, does this work in low temperature? We never designed this to work in low temperature. We just took 65 gigahertz modular, dunked it in 4 Kelvin, like so, 77 Kelvin doer. We have a better version when I brought my beer cooler and put it there, and then we dunked it multiple times and tested, and it works. Not only doesn't break, which is actually non-trivial, because the weakest spot is polymer that's used to couple fiber to lithium niobate, but actually gets better. Okay, so this is electro-optic effect, and then we put it in in a octo cube, so down to 4 Kelvin. And basically, this is just transmission electro-optic measurement for different temperatures, that nothing changes. Bias point, maybe this is of interest to folks. Oops. So this is dirty secret. So this is electro-optic modulator by HyperLight or anybody else. This is optical signal, and this is voltage here, right? And so you park modulator here, it's called quadrature. And so you're hoping, in ideal case, that this transmission
Oh, yeah.
Yeah, so very, very nice work, a lot of work. So it's very hard to keep track of. So when you did the DAC with the light, what's the speed that you can run at?
This is the speed. So we were limited by that. It was limited by AWG that we used, which is 96 gigawatt. The bandwidth of the modulator is, I mean, this one probably was like 56 gigahertz. Actually, we didn't that. Like it was like 50 gigahertz, probably exceeding that. And the DAC is 96.
Okay, thank you.
Thanks, Marko. Great talk. I had a question about the frequency converter results that you had. I remember the molecule, the new paper. Yeah. Oh, no. The Rigetti one, the one with Rigetti. Yeah. So So I remember from when we were trying to do these experiments with the photonic molecules, there was, you would put power into these things and then they would just keep drifting. And it was worse at low temperature because I guess you would generate charges, photovoltaically, and then they would like cause this electro-optic effect. So I was wondering if you got around that, or what was?
For this reason, we saw we would be writing grading inside. Further attractive. And then there were something like, and so in order to avoid this, we basically done off. Run experiment. I mean, not crazy, but it's not like big, it's like some kilohertz or something like that, where you do, you do production that also we're considering going plus minus minus plus. Reverse bias is almost like AC combo. That's the easiest way to AC.
So that doesn't limit you. You can reverse that effect. Is that what you're saying?
And also, could be also because it matter software. So, I mean, not sure we can have a paper is the same. We find out that it's something more standardized, then it looks definitely a difference in different vendors. And so I'm not sure if it's more dramatic than that. There's a particular moment. I'm not saying we can have a software for a moment in time. You see from
So first, great talk as always. What's the limit on transduction efficiency? I guess if you improve your Q factor, you said it could be 200 million or something. I don't know. Okay, well, I know that, but for lithium niobate, can you reach that considering the limits on Qs and everything?
Yes, in most of the people, in most of the time, like in theory, yes. Are we going to be? That's probably not. In this paper, actually, there is, or do we want to get there? I mean, yes, but is it worth it? I don't know, right? So we talked to Leon, there's this like VLCD type protocol that you want to use for not direct induction, but entanglement and that apparently becomes quite important.
Okay.
So currently 10% is including Q, optical Q, controlling convection power, including without any superconductor. And 10% beyond that, before it needs to be designed.
Okay.
One of the issues is extraction efficiency. So the coupling brings to the simplified property. There is also extraction efficiency, efficiently put on in and out with optical microwave, and that basically there.
Okay. Okay. And
guide, and then you have to
okay. And the other question is, where is the foundry? Is that your foundry in the company, or it's use different foundry?
No, it is a commercial foundry. It's not in the US, and it's also not in China.
Okay.
This is something that people worry about. We're hoping and worry about. So,
okay.
It is commercial scale foundry that we have our tool with that, and we develop the process.
Okay.
But they own the process. They own foundry.
Okay, but it's HyperLight related, right? Yeah. Okay, so if someone wants to use the foundry, they go through HyperLight. Okay. Good. Sounds good. Okay, good. Yes. Okay, good. Thank you.
If there's no more question, let's thank Marko again for